That's the 2 transistor flasher circuit. The battery powers up and it charges up this capacitor, and just for a brief instant this capacitor looks like a dead short circuit. Once the capacitor has charged up, it starts to look like a battery. So we've drawn a symbol there looking like a battery. That becomes important later on in our explanation. TR1, transistor 1, also known as Q1, and TR2 or Q2. Those are 2 NPN transistors, 9 volts up there, and we've got 0 volts over here. We've got 2 LEDs over there. These are light emitting diodes. Cathode side, anode side, cathode side, anode side. We've got 2 electrolytic capacitors over there. We've got a current limiting resistor over here, which can be between 680 ohms and 1 kilo ohm. 680 ohms or 1 kilo ohm, somewhere around there. You could even drop this value lower if you want the LEDs to be a bit brighter. Maybe you can use a 470 kilo ohm. It's important to note that a wide range of parts will work in this circuit. So we have a NPN transistor here, which is a 2N3904. 2N3904. So those are our NPN transistors. This is our base connection, this is our collector, this is our emitter. Base, collector, emitter. These are low value resistances, but over here we've got a higher value of a resistance. We could use a 100 kilo ohm resistor here and a 100 kilo ohm resistor over there. If we're going to use 100 kilo ohms there, then we can use a 10 microfarad electrolytic capacitor over here and a 10 microfarad electrolytic capacitor over there. You'll notice the circuit is quite symmetrical. We can fold the circuit over. The circuit is mirrored. So if we were to change this value and this value, also this value and this value, to maintain that symmetry, we're going to have these LEDs flashing off and on at the same rate. What that might look like in real life, we've got the LED switching on for say half a second, switching off for half a second, switching on for half a second, switching off for half a second. If we look at the circuit, there are 2 LEDs, 2 transistors. So this being TR1, then this would be R1, because this resistor is attached to the base of this transistor, and this capacitor would be C1, because it's attached to the base of this transistor. So by implication, that means that this TR2 transistor is connected via its base to this resistance here, can be R2. Then this capacitor can be C2 because it's attached to transistor 2. This might be the waveform, for example, of LED 1. Why is this LED 1 here near to C2 and R2? Because LED 1 is switched on and off by TR1. So this LED would then be LED number 2, because it's switched off and on by transistor 2. Okay. So If this graph represented, say, LED 1 coming on, going off, coming on, then the other LED might be doing the opposite. So when the one is on, the other one is off. Okay, this being on for LED number 1, and this being off for LED 1. Then this might be on for LED number 2. So that's on for LED 2 in this position, and here it's off for LED 2. And what you'll see is when this one is on, this one is off, and when this one is on, that one is off, because they are alternating. So let's have a look at what that looks like. So this is our breadboard, and we're just applying power. So we've applied power over here, down the rail here. So let's go back to our 2 LED flasher circuit explanation. Here we've got our reference schematic diagram. If we were to put a voltmeter into this picture, we could have test points. So for example, we might have test point A. But you'll see here we connect it to 0 volts, so this might be the black lead of the multimeter. The next thing we could do is we could identify some more test points. Just as we're going through this explanation, we can refer to those as we talk about what's going on. So we might attach the red lead of our multimeter over here, and we could call this point test point base 1. So this is a test point for the base of the transistor, and it's the base of transistor 1. So it's TPB1, test point base 1. Then we could attach a multimeter over here, and this test point might be called test point collector, so TPC 1. So it's test point on collector 1 because it connects to the collector of transistor 1. Now, by implication, we could attach a test point here, but electrically it should look the same because this is connected to there. So this is also test point B1. So I'm not going to write anything there. Now we can attach our red lead of our multimeter to the circuit over here. And this point would be test point B base 2. So it's test point on the base of transistor 2. Same principle would apply here, where we could attach our multimeter, the red lead, all the while the black lead is connected to 0 volts, because we're just taking voltage readings at various places in the circuit. So this one would be test point C2, because it's the test point on collector of transistor 2. So over here, again, if we were to attach our multimeter over here, it would be the same as attaching our multimeter to test point base 2, because that is connected. So let's just clarify one thing for those of you who are relatively new to electronics. If you're looking at a circuit diagram and you see like that, that is not connected. And I'll explain that in a moment. But if you see this, then you definitely have a connection. That means connected, not connected. What I normally do to help my students understand better is if this is a wire going this way and it's not connected, I'll do a jump over like that. So this is not connected, and this is connected, and this is not connected. So I hope that clarifies it for you. So what you'll see in my circuit diagram is wherever wires are joining up to things, I take a bit of effort and I put a nice big dot so you can see there's a connection. No connection, folks, no connection. So these wires are just passing by each other. So when we apply power to this circuit diagram, what happens is the bases of both of these two transistors start to charge up through the path here, because we're going to talk about conventional current. Now we all know from Electronics 101 that current flows from plus 9 volts up here. It's going to flow through these resistors. Conventional current, it's going to want to come to minus or O volts, or sometimes represented as earth. Okay, so that's the normal route that electricity is going to want to follow. We also know that electrons flow from O volts or ground or minus or earth. Electrons will want to flow up to plus. But for now, suffice it to say that the current starts to flow through these resistors. And what happens is this point here, which is the same as test point on B1, starts to charge up through this resistor to 9 volts. At the same time, test point B2, test point base 2, which is the same as this test point, starts to also charge up to 9 volts. What we discovered previously is that the voltage here will go up to 0.7 volts, and the voltage here will go up to 0.7 volts, at which stage the transistor will switch on, and then a whole lot of other stuff starts to happen. But for now, suffice it to say that the 9 volts that's applied here and comes down through here will reach 0.7 volts switching on this transistor. At the same time, or maybe not at the same time, but at a similar time, this transistor is also going up to 0.7 volts on its base. Now it's reasonably safe to assume that these resistors, even though they are nominally 100 kilo ohms, maybe this one is, let's say, 98 kilo ohms in terms of its 1% or 5% tolerance on the part, so it's not quite 100 kilo ohms. And then this one over here is maybe, I don't know, a little bit more. So maybe this one is 101 kilo ohms. So it's not exactly 100 kilo ohms, and this is to do with the quality of the part, the manufacturing process, where no two things are absolutely perfectly identical. Before power is applied to the circuit, we could represent these transistors as being in an off state. In other words, there's no connection between the collector through the base into the emitter on either side. But what's going to happen is when we apply the voltage, assuming that this resistor has maybe a slightly lower resistance than this resistor, maybe this base will reach its bias level and switch this transistor on. Let's just do that there. Okay, so this transistor comes on in a fraction of a second before this one comes on. Essentially what happens is this point here would have been charging up. So as these were charging up, these would also have been charging up through this resistor and this LED. And there is a voltage drop through an LED, so that's another thing we have to be aware of. But this low resistance resistor here would have been charging up quite quickly. We're measuring with the black lead of the multimeter over here and the red lead of the multimeter over here on a volts range. And the voltage here would have quickly, at the same time as these bases were charging up, the voltage on test point collector 1 would have gone up, and that level would have been not quite 9 volts because of the voltage drop through the LED. Because of the lower resistance here than here, this base would have switched on this transistor. In the instance before this transistor comes on, because the base has reached 0.7 volts, both of these capacitors would have charged up to the rail voltage less the voltage drop through the LED. And that voltage would have been read over here at test point C1. But now as the base reaches 0.7 volts and the electronic switch action of the transistor comes into play, in that moment where this transistor is fully biased on, these junctions here would have closed the switch inside of this transistor. It's not a physical switch, it's an electronic switch. And effectively what that means is there's a dead short circuit between the collector and the emitter, and there's current flowing through here. So instantaneously, the voltage at test point collector 1 drops to this voltage down here. Now remember that the voltage down here is 0 volts, because all along this rail to that point there, it's all 0 volts. So the moment you close the switch inside the transistor, this point drops to 0 volts. But now the capacitor was previously charged up. So the capacitor at this point is looking a little bit like a battery. In other words, it's got a little bit of electricity stored up inside of itself. This is where a fascinating thing happens in this particular circuit. Because test point C1 is dropped to 0 volts, whatever voltage was across this capacitor here is now pushed quite deeply into negative territory, because if you have a voltage here, a potential difference across the plates of this capacitor here, and now suddenly you have 0 volts over here, that forces whatever voltage is here to read as a minus voltage. And you can see that minus voltage appears over here, but it also appears over here. So the minus voltage, whatever potential difference or voltage was present on this capacitor here, is now pushed into negative territory, because you've got 0 volts here, and this capacitor cannot discharge instantaneously. It does take a few milliseconds to discharge. So over here you see a negative voltage, and over here you see a negative voltage, which switches off this transistor. Because remember, when this little oscillator circuit starts up, you see some strange stuff, like it looks like both transistors come on, but the one is only on for like a very brief instant. And that's what's happening here, is as this transistor comes on and it forces this down to 0 volts, and the capacitor forces this point, and which is connected to these points, down into deeply negative territory, that immediately switches off this transistor, which might have actually come on for just a brief instant as the whole circuit powered up. But now what happens is, with this transistor in an open contact or off state, if we continue to compare this transistor to a physical switch, that means over here we might see plus minus somewhere in the region, depending on the condition of our battery. We might see about, say, 6.45 volts over here at test point C2, because remember, test point C2 and this point, they're the same point, they're all connected. So now this capacitor starts to charge up. At the same time that this capacitor starts to charge up and this transistor is acting like an open switch, the base point is again, because as long as power is connected here to there with our battery, these points are always going to be charging up until they're knocked down. Even as this transistor came on and this went to 0 volts, pushing this down to minus 4, 5 or 6 volts, if this transistor had in fact started up when the circuit started up, that would have been at 0 volts. But the moment this transistor on the base was knocked down into minus territory, this would have opened up the transistor in terms of comparing it to a switch. It would have turned it into an open contact type switch, and then this voltage here would have started to climb up to a higher voltage. But at the same time, this resistor here, this is resistor R2, which applies to the base of transistor 2. This resistor would have allowed current to start flowing through here and pulling up the voltage at test point base 2. It would have been pulling the voltage up and up and up. Suddenly this transistor's base would have reached 0.7 volts. And as this transistor's base, test point on base 2, would have reached 0.7 volts, this transistor would have switched on. Now as this test point on base 2 would have reached the magical voltage, 0.7 volts, and it would have been forward biased, then again, closed contact switch here, which would have knocked this voltage here down to 0 volts over there, and then whatever voltage it would have charged up to over here would have been pushed into minus territory, and that would have had the action, because this side of the capacitor is obviously connected to there, but that's connected to the test point on base 1. So that deeply minus or negative voltage would have switched this transistor off. So then what would have happened, we'll just do that like this, we would have had an open contact switch on this side again. What you've seen so far is they both came on rather quickly, but this one came on a few instants before the other one, and as this one came on, that went to 0 volts, and that pushed this into deeply negative territory, which would have forced this transistor off. As this transistor came on, then what would have happened is that voltage there would have dropped to 0 volts. It would have forced whatever voltage is across this charged up capacitor, would have been forced deeply into negative territory, which would have pushed this voltage right down into negative territory, which would have switched off this transistor. Now this transistor is in an off state, and what we need to remember to mention is that the moment this transistor is a closed contact or an on switch, current can flow through this path and the LED lights up. So when this transistor has been forced down into negative territory and it's no more biased forward, so we don't have the bias voltage here to switch it on, this LED is off. Let's just say there's no current flowing through this LED, so this LED is not lit up. So here we've got current flowing through here, we've got 0 volts there, and this LED is making some light. Again, what starts to happen is at the base, which is connected through this resistor up to 9 volts over there. Again, what starts to happen is this point is charging up to 9 volts, which is connected to this point, which is connected to the base. Essentially, this transistor is waiting for this point to come up again to recover to 0.7 volts. And when this base recovers to 0.7 volts, what happens? The transistor starts to conduct again. And as this transistor is now conducting, the LED lights up on this side. And then what happens is, as this comes on, the voltage here, which would have gone up to, say, around 6 volts maybe. So this voltage that went up to 6 volts at this point while this was open drops straight away to 0 volts as this transistor comes on. So this transistor is now on and it's conducting. That point is 0 volts. In the meanwhile, this capacitor would have charged up. So it had a voltage across the plates. But as this switch closed contacts, this capacitor can't discharge as quickly as the contacts on the transistor closed. So what happens is you've got 0 volts here, which forces the voltage across this capacitor to drop at this point, which is connected to that point, into deeply negative territory. And when this goes negative, then the transistor becomes like an open contact switch. And the moment this transistor becomes like an open contact switch, this voltage here rises up from 0 volts, because when it was a closed contact switch, the voltage here and the voltage measured there is the same. But with this open contact situation, the voltage rises up from 0 volts up to around 6 volts, and that now starts to charge up this capacitor. What would be useful at this stage is to bring an actual circuit in here and to connect up the voltmeters and to observe some actual voltages. In other words, observe the circuit in operation with voltmeters in the circuit, so we can have a look at what these actual voltages are at these test points. So what we're looking at here is we've got the white lead, which is on the common of the multimeter, and we're on the 20 volts range. So the red lead of your multimeter, in this instance it's a gray lead because I'm just using breadboarding wire, and the plus lead of the multimeter that's active on this side is connecting to test point collector 1. In other words, the test point that's connected between the collector and the cathode of the LED. And you will see the voltage there is going from around about 0 volts up to 5.7 volts-ish. I've got this battery which might have more juice in it than this yellow battery. This 9 volt battery's got 8 volts. So let's put this lead back to test point collector of transistor 1. And you can see it's fluctuating between 6.2 volts going down almost to 0. So if we had a 9 volt battery that was brand new, we'd probably be seeing a slightly higher voltage at that point. But now we've got this other meter here which is currently not doing much. So let's connect this meter here to test point A. So we're connecting the blue lead or the black lead of your multimeter. If you're following along at home, we're going to now connect this. So I'm just looking for a wire. I take a male to male. I'm going to take a red one. I'm going to bend the point over so that I can just stick this into the banana plug sized hole on the multimeter, because you can't really do this with the leads, with the normal leads of a multimeter, because They've got those pointy probes that'll just fall over if you let go. Now what I'm going to do is I'm going to connect this wire here. So now I've connected this wire. Let me just see if I can move the lighting a bit to get a better result. Okay, I think that's quite successful. So what we are observing now is we've got this meter is connected to, here comes our diagram, if I can get it in there. So we've connected our multimeter to test point collector 1 over here. And we've connected the meter on this side to the test point of base 2, but we've connected it probably more like there. And so now we can see how when this transistor comes on, it pushes this voltage down to 0 volts, and at the same time, on the other side of the capacitor, we've got this deeply negative result which switches that transistor off.